I've been excited to give this talk for a while now because lambda calculus is a term that I've heard throughout my career and just never took the time to look into it and see what it really was. And I finally did that a few months ago and was amazed. I'll skip this. So what is lambda calculus? Well, it defines a bunch of concepts that are very fundamental to functional programming. One of those is first-class functions, and that's functions where you can pass other functions to it, and those functions can return new functions. And then also the concept of currying, where instead of having a function that takes multiple parameters, each function only takes one, and there's a sequence of them that you call through, and you'll see that multiple times in this talk. So the purpose of lambda calculus was to study how functions can interact with each other, and while you can calculate results, the way that it happens is not very efficient at all. It's not the way you would want to do it. But keep in mind that this is something that was invented in the 1930s before they had computers to actually test this out on. And so it was very theoretical at the time. Lambda calculus is Turing complete. And so anything that can be computed with lambda calculus. I think it's useful to compare this to a slide rule. You don't need to use slide rules anymore. We've got calculators and they do a great job as a substitute for a slide rule. But slide rules are still interesting in learning how it is that they work and thinking about logarithms. And lambda calculus is much the same way. You don't need to write software that works in exactly this way, but it's still fascinating how much you can do within the constraints of lambda calculus. I won't spend too much time talking about history, but as you might imagine, there are mathematicians from long ago that researched things that ended up becoming a part of lambda calculus. One of those is the word combinator, which I was surprised to find has two different meanings. So one meaning of combinator is a function that only uses what's passed to it, what we would call a pure function now. And a second meaning is that it's a first-class function, one that can have functions passed into it and can return functions. So it's combining functions to build a new one. The creator of lambda calculus was Elonzo Church, and he happened to be the PhD advisor to Alan Turing, which is interesting. Here are some basic concepts that you need to know to work with lambda calculus. And so the first is that you have a concept of a variable, which in lambda calculus is always just a single character name for this variable. You never really explicitly assign a value to it. It's just there as a placeholder for some value that someday you might know the value of it. And there are two kinds of variables. They can either be bound or free. And in a couple more slides, we'll look at the distinction between those. Then there's a lambda abstraction, which is really an anonymous function. And this is a key thing, that functions in lambda calculus do not have names. So you can't call them by name. You have to have the full function definition, and then you can feed arguments into it. And the syntax for this is to use the lambda character itself. And so you see here the lambda character, and then there's the single parameter that it takes, and then a period, and then all the expressions that follow are part of the body of that function. And throughout the talk here, you'll see that I'm showing side by side what the syntax is in lambda calculus and what it would be in JavaScript. And I've tested all of this with JavaScript code. So in JavaScript, I can write an anonymous function just with this arrow. And so I have my parameter, an arrow, and then the function body. Another thing to know is that when it's evaluating the body of a function, it does it from left to right. And the only thing that you have in lambda calculus are functions. And so if I look at an expression like this is a function that takes a parameter x, and then its body is abcx. But how is it going to evaluate that? So as I said, the only thing you have are functions. So a, b, c, and x are all functions. And so I pass b to the function a, and that gives me a new function. And then I pass c into that function, and I get a new function. And then x is passed into that function. Sometimes you'll see a shorthand way of writing this. So instead of saying lambda x, lambda y, lambda z, I could write lambda x, y, z. But this is just a shorthand. It is not a function that takes 3 parameters, because lambda calculus only supports functions that take 1 parameter. Now we know how to define a function, and then if I want to apply one, I just specify some arguments after the function. And so in Lambda Calculus, I'd have the definition of my function in parentheses, and then outside of that, the arguments I want to feed in. And then in JavaScript, it would look like that. When I'm doing this in JavaScript, I have to be explicit that this is an argument going into that function. And what I get back is another function. And so this is the argument going into the second function. And then this is the argument going into the third function. There are a lot of things that are not defined in Lambda Calculus. There is no syntax for values like Booleans or numbers or strings. There's no operators that work on those types, and there's no built-in functions. Everything is just a function that you define. However, all of those missing things can be defined with just the concepts that we saw on the previous slide, and that's what makes Lambda Calculus so amazing. I mentioned that there are two kinds of variables, bound and free. So a bound variable is one that is a parameter to a function. It represents an input to a function. Free variables are not parameters to a function. They come from the quote-unquote environment, and so they're kind of like globally known things. And so I think it's useful to look at a few examples in this table at the bottom. So if I look at this first function, it's a function that takes x and it returns the result of adding x and 1. Now, I said that there's no operators, and there aren't. And so here we're just pretending. Let's just pretend for a minute that we had a function plus, that I could give it two numbers. So here, x is a bound variable because it was passed into the function, and I don't have any free variables. In the second example, I pass in x, but I don't even use it in the body. Instead, I use y, which wasn't one of the parameters, so that has to come from the environment somewhere, and that's what makes it a free variable. I don't have any bound ones. The next example is interesting because there are two distinct uses of x. First, I have a function on the outside that takes the parameter x, but inside the body, it's defining yet another function that happens to also call its parameter x, but those are not the same thing. And in fact, it would be perfectly fine for me to rename that parameter, so I might as well call it y instead and replace it. And we're going to see a name for doing exactly this coming up in just a bit. And so in that function, you would say that x and y are both bound variables because they're coming in as parameters to those functions, and I don't have any free variables in that example. So there are 4 evaluation rules that Lambda Calculus defines, and so if you want to be very precise about what's happening at each step in an evaluation, you would say that they're one of these 4 types. So an alpha conversion is what we just saw, where you're just renaming things. And so if I've got this function x that just returns x, well, I could write it with y's, and I didn't change anything. I just renamed the parameter. Also, this function that's a bit more complicated has 2 things coming in, a function and some value. And so it just applies that function, whatever it is, to x with 1 added to it. Well, if I rewrite that and I change the f's to g's and the x's to y's, I haven't changed anything. It's still a function doing exactly the same thing. So that's an alpha conversion. The delta rule is where you take an expression and just evaluate it. And so again, if I assume that I have this plus function that we'll be defining coming up, I could just evaluate that to be 3 and replace it that way. So that's a delta rule. A beta reduction is where I'm applying arguments to a function, and so I get the result after I make those substitutions. In this example, I have this function that takes x, and it's going to return what I get when I add the x with the 3. And so here I'm passing something in, and so this 2 becomes the value of x. And so I can simplify it to this now, and of course I can evaluate that to 5. Here's a function that expects 2 arguments, some function and some x value. It's going to add 1 to the x and pass that into f, and whatever that returns is going to be the result. And so let's look at applying that. So here is that function, and I have to pass it 2 things. So here's my first. It's a function that takes some number and multiplies by 2. And then the second argument is just 3. So if I take this function here and I substitute it in place of f, I get this. And then here's the x plus 1 part. I substitute the 3 for that x, and now we're down to here. Okay, so there I've done a beta reduction. Now I can apply the delta rule to evaluate this piece. That's clearly 4, and so I can just do that substitution. Now I apply the beta reduction again, and I take this 4 and I put it in as the value of x. And now I get times 4 and 2, and then finally I apply the delta rule and I get an 8. A very formal run through of how you could apply arguments to some function. The last one of these rules is an eta conversion. And this is where you take a function that has an explicit parameter and you turn it into a new function that has an implicit parameter, or what we also call a point-free version of a function. So here I've got a function that clearly takes a parameter x and returns x plus 1, but I could just rewrite it like this. And the reason that this works is that you know that plus is a function that requires 2 things. So if I only give it 1, then surely what I get back is a new function that expects the other thing. And this is really getting into currying. Now we're done with kind of the formal presentation of lambda calculus, and we're ready to get to some application of it. And so I mentioned that there's no syntax for representing Booleans or numbers, and so we have to make this up. And because the only thing you have in lambda calculus are functions, I have to pick a function to represent true and another function to represent false. And as we're going to see in a bit, I have to pick a function that represents 1 and 2 and 3. I can pick anything I want for these functions, but it's good that Elonzo Church found some functions that turn out to be very convenient for doing things like defining Boolean operations like not and or functions for numbers that make it really convenient to add and subtract and multiply and so on. And so what did he come up with? Well, for the true function, he said, well, let's represent that by this function that returns another function that is going to give me a result. What's really happening here is that I have 2 things coming in, and no matter what I give it, it always returns the first one. Now, I named these T and F representing true and false, but it doesn't matter what I name them. The point is, here's a function that essentially takes 2 parameters and always returns the first one. And false is the opposite, takes 2 parameters, it always returns the second one. With that in hand, we can start to do some interesting things. When I implemented this in JavaScript, I couldn't call these functions true and false, so I just added an underscore to the end, because those are keywords in JavaScript. So now that I have these definitions of true and false, could I write a function where I pass one of those functions into it and it returns the opposite one, a not function? The way this works is that you pass one of your Boolean values in, so either it's the function representing true or false, and that function wanted 2 things, and so I give it 2 things. I give it false and true. Well, if the one I passed in was true, true always returns the first argument, so it gives me false. But if I gave it the false function, it always returns the second thing, and so I get true. Okay, and this is just kind of walking through that logic in lambda calculus. Now, how would I do an and? Well, this is interesting because since the true function always returns its first argument, if the first one is false, I know the result has to be false. And so in this function here, suppose it's false, I know the result has to be false. Well, the false function always returns the second thing, and so I get false. But what if it's true? I always return the first one. Well, the first argument that I'm passing in here was actually the second one, so I'm just saying, well, whatever the second one is, that's what it'll be. If it's true, the result is true. If it's false, the result is false. And as you can imagine, or is very similar to that. We just reverse some things around a bit. And we say, if the first thing is true, I know the result is true. I can stop. So true always returns its first argument, true. But if it's false, I just return the second thing. So either it's true or false based on whether the second argument was true or false. Just as a quick diversion here, I want to show you that I have implemented all of this in JavaScript. Right here, I'm going to run all of my unit tests that test everything I'm going to show you here. So let's see how long it takes to run all this. Boom, it's done. This is in large part due to the fact that the Bun JavaScript engine is really lightning fast. We're done talking about Boolean values and we're ready to talk about numbers. And so we have to come up with functions that represent a number. And what Elonzo Church came up with are called church numerals. And basically the idea is you pass it a function and some value, and the number it represents is how many times it called that function. So in this first one here, I give it a function and a number, and it just returns the number. So it didn't call the function at all. That's 0. This one calls the function one time and returns its result. That's 1. Here's 2. Here's 3. Okay, and here's the way you would write that in JavaScript. Another interesting side effect of this is that you can use this representation of a number to say, I want to execute this code this number of times, because it's calling itself that number of times. And so it's kind of a way of doing looping in Lambda Calculus. That's a very convenient way to represent numbers because it lets us do some pretty interesting things. And so we'll build up to this slowly. The first thing I need is a way to find the successor of a number. So the successor of 4 is 5. It's just the next one. Well, since a number is represented by calling a function some number of times, the successor must be calling that function just one more time. In this definition here, n is the number I want to find the successor of. So let's suppose it was 3. So it's calling this function f 3 times, but then this f right there says, do it one more time, please. So that's my successor function. And this is very much related to what are called piano numbers by Giuseppe Piano. And he came up with this idea that you can get all the natural numbers if you just have a definition for 0 and a way of finding the successor of any number. And you just keep calling successor over and over again. Now, with that in hand, it seems like, boy, it'd be pretty easy to define a function that gives me the predecessor. Predecessor of 3 is 2. That's easy, right? Well, it wasn't easy. In fact, Elonzo Church could not figure this out. But one of his students figured it out for him while he was in a dentist chair waiting to have some wisdom teeth removed. At least that's the way the story goes. So what he came up with is, what if we have a pair of numbers? Let's start with the pair 0, 0. And we'll say, we need a way to get the next pair. And so the way I'll get the next pair is I'll take the second number in the previous pair, which is 0, and I'll make that be the first number in my new pair. And then the second number in the new pair will be the successor of that one. And I'll just keep doing this a certain number of times. And then when I'm finally finished, whatever is the first number in the final pair is my predecessor. And so let's take a look at an example of this. What is the predecessor of 5? So I start with 0, 0, and I turn this crank 5 times. So the first time I do it, I take the second number, it becomes the first, and this is the successor of that. Then this becomes the first, and I get the successor, and this becomes the first, get the successor, and keep going. After I've done it 5 times, if I just take the first number of the last pair, that's the predecessor. So you can see that the reason that this works is the delay in incrementing the first number. I didn't do it the first time, but then I started incrementing. Amazing to figure this out in a dentist chair. And also an incredibly inefficient way of finding a predecessor of a number. In fact, implementing this in Lambda Calculus is a little tricky because you actually need to write 4 helper functions to do this. So the first thing I need is a way to represent a pair, because that was what that was based on. And so I'll say that a pair is when I pass in the first and the second value and I give it a function. And what I get back is that function applied to those 2 things. And I'll just pretend like this represents a pair. Well, if I have that, then I can find a way to write a function that gives me the first value of a pair. And so that's just give me the pair, and I'll apply the true function to it, because true always returns the first of the things you gave it. And second is very similar. I give it the false function. That always returns the second thing. So I'm reusing those functions from before. The next thing I need is a way to get the next pair. And so that's what this phi function is doing for me. All I do is I pass in a pair and I say, okay, make me a new pair where the first number is the second number from the one you passed in, and the second one is the successor of that. And so now we have JavaScript implementations of those 4 functions, and I'm ready to combine them to build this predecessor function. And so the predecessor function says, give me the first number that you get after you apply the phi function n times to this pair that starts off 0, 0. So the phi function gives me the next one, and the next one, I just do that n times. And when I'm done, I take the first number, and that's the predecessor. Now, there is another way that you could write this. You could write it like that, but I cannot wrap my head around what is actually happening there. But actually, if you're being technical about this, you kind of have to write it that way, because I told you earlier that Lambda functions do not have names. So I can't even really do this in Lambda Calculus. Really, I have to substitute where you see these names, the actual function definition, and then it would end up looking something closer to that. So now we've got successor, we've got predecessor, we're ready to do some math. So let's talk about adding numbers. How could I write a function that takes these weird church numerals, these functions, and adds them together? So if I give it numbers like 2 and 3, I need to get back a function that calls the function you give it 5 times, because that's the way we're representing numbers. Okay, and so I could write add this way, that you give me one of those church numerals and you give me another one. And so what I'll do is I'll start with n, the second number, and I'll get its successor m times. Okay, so if I want to do 3 plus 2, then I say, okay, let's call this function. We'll give it our functions for 3 and 2. And so this is going to substitute in here. So m was the 3, and then we've got the successor and the 2. Applying the successor 3 times could be replaced by this. And now I get the successor of 2, which is 3, the successor of 3, which is 4, the successor of 4, which is 5. This is order n. That's really bad for addition. It's got to go through a lot, but it works. And it's amazing that we're doing this with just functions. How about subtraction? Addition was just iterating successors, and here we're iterating predecessors. And so I say, let's start with the first number, 5 in this case, and then I want to ask for its predecessor 2 times, and I'll get down to the 3. So that's the way you would write it. This is even worse. This is order n squared, because the predecessor function was order n, and I'm doing that n times, but it works. Multiplication can be seen as iterated addition. I just say, let's start with 0, and I take the number that I want to multiply, and I add it that many times. Okay, so if I want to do 4 times 3, and I look up here, I want to add 3 to 0, but I want to do that 4 times. Multiplying 4 and 3 turns into this expression. 4 times adding 3 turns into that mess. And then I start breaking it down one at a time. Adding 3 and 0 gives me 3. Adding 3 and 3 gives me 6. Adding 6 and 3 gives me 9. Adding 3 and 9 gives me 12. Order n squared for multiplication. Again, amazing. How about exponentiation? I want to raise some number to another power. Well, this is just iterated multiplication. I start with 1, and I take the number and I keep multiplying over and over again that number of times. So it just says, take the second number, which was the exponent, and I want to multiply the first number by 1, but then keep doing that n times. And so 2 to the 3rd power, I put the 3 on the outside, I'm multiplying 2 by 1. So doing this 3 times gives me multiply 2, multiply 2, multiply 2, and the 1. So now I evaluate this. 2 times 1 is 2. 2 times 2 is 4. 2 times 4 is 8. And I've got my exponentiation. There's an alternate way to write this, which is much easier and really surprising, is that if I just put the lambda calculus function for n here and then pass it m, it ends up doing the same thing. And so this is kind of walking through how it ends up with this representation of the number 8. I could take 2 of these lambda calculus functions and compose them. Suppose I've got a function that adds 2 to a number, and I've got another function that multiplies a number by 3. Well, I can put these things together. I just take my two functions that will eventually be given a number that they're going to operate on, and I just do this, and that's the composition of two functions. Now we're ready to talk about how you could possibly implement something like recursion in lambda calculus. And this is tricky because, as I said, lambda calculus functions don't have a name, so how would it even refer to itself? So you need some special magic to make this happen. And so before we get to the actual magic, we have to lead up to it by talking about fixed points. A function has a fixed point if you can pass it a value and the result is the exact same value. And so a simple example of this is the square root function. The square root of 1 is 1. But interestingly, other functions like cosine have a fixed point too. If you put this number 0.739 so on into the cosine function, you get back the same number, well, within rounding errors. But there is a point along the cosine curve where you get a matching value. And lambda calculus also has a fixed point. It is this function right here. I pass in a function x, and what I get back is that function applied to itself. Why is that a fixed point? Look at this example of applying that function to itself. Now, what would happen if I did this? Well, this is the argument, and so it means that this exact expression has to be substituted for this x and for this x. But if I do that, what I get back is exactly this. It just repeats forever. And this thing is called the omega combinator. It's interesting, but it doesn't do anything. It just keeps evaluating till the end of time. What could we do with that? Well, to do anything really interesting, we've got to have a way to stop, right? When you do recursion, you need to have some test that says I'm finished recursing. And we're leading up to being able to define a factorial function, and the factorial function needs to stop when I get to 0. So how could I test a number to see if it's 0? Well, the function for 0 happens to be exactly the same as the function for false. It always returns its second argument. If I pass in the representation for the number 0, this is going to return true because that's the second thing. But what if it's some other function? Well, what I'll return is this function that takes some number, whatever it is, and returns false. And so this means that if I ask, is 7 0? It's going to say, is 6 0? Is 5 0? And it iterates through all those numbers. And finally, when it reaches 0, it doesn't return true because this says it's a function that no matter how many times I call it and no matter what I pass, it always returns false. So if I ask if 7 is 0, it's going to say false, but it takes a while to get there because it has to crank on that 7 times. So that's order n just to test to see if a number is 0. But we need this is 0 function in order to implement a recursion. I can't call a function directly because it doesn't have a name, but I can use this thing called the y combinator. And the y combinator is very much like the omega function. It just differs in that we've thrown in this f here to say that while it's iterating over and over, could you please actually do some work? Do the work of this function that I'm passing into you. So this was discovered by the mathematician Haskell Curry. In JavaScript, you would write it this way. So now I have a way to recurse in lambda calculus and actually do some work that's defined by that function f. But what should the function f be? Well, that depends on what you're trying to achieve with your recursive function. So if what I want to do is compute the factorial of a number, then this is the f I need that I'm calling facgen there. It's generating a factorial. This function takes in another function and then the number that I'm computing the factorial of. And then I just test to see, is the number 0? And if it is, then I return a function that returns the value 1, because factorial of 0 is 1. But if it's not 0, then what I want to do is I want to multiply that number. Let's say we're doing factorial of 3. I want to multiply 3 by whatever the factorial of 2 is. And so I get the predecessor of 3, which is 2, and then I call that function. And so it's doing the recursion here, and it keeps doing that multiplication. So that's what I need to generate a factorial. And then if I feed that into the y combinator function, now I can do this thing recursively and finally give me the result that I want. And so 3 factorial expands out into this. And that's because 3 is not 0. And so we focus just on that side. And so I'm multiplying 3 by that factorial function on the predecessor of 3, which of course gives me 2 times the predecessor of 2. Then I get 1 times the predecessor of 1, and 1 times this function on 0. That gives me 1. That's this part right here. And so now I've got 1 times 1, and 2 times 1, and finally 3 times 2, and I get the result that I was after. 6 is the factorial of 3. Now, the interesting thing about this is that I'm not really using the y combinator here. I'm using another closely related function called the z combinator. And the difference between them is that if I was using the y combinator, right here, I would just return 1. And right here, I would just return this expression instead of a function that evaluates that. Now, the reason that I'm doing it this way is that I'm writing this in JavaScript, and JavaScript, like most programming languages, is not lazily evaluated. If I didn't do it this way, every time I run FactGen, it would evaluate this expression and that one, and it would never stop. And why didn't all the articles I was reading about Y Combinator tell me about this? It's because they assume that you're using a language like Haskell, which is lazily evaluated automatically, and you don't have to think about it. It won't just call a function until you ask for the result. So I have to use the Z combinator with most programming languages to actually get this to work. And that's why there's these extra parentheses out here, because I'm getting one of those 2 functions, and then I have to actually call it to get the result. You can represent linked lists with Lambda Calculus. You just need functions to represent how do I create a cons cell, which is a thing that has a head and a tail. You need a way to get the head or the tail that are usually called the car function and the could'er function from Lisp. And you need a way to represent what it means to be at the end of a list, a nil value. And so I can write functions for those, and I'll just say cons is when you give me 2 things, a value for the head and the tail, and I'll give you a function that kind of wraps those up. This is just like the pair function that we saw earlier. And then this car function is just like my first function that we saw for pairs. And the could'er function is just like that second function. And then I'll say, well, nil is a function that no matter what I give it, it returns this null value. And it's null here because that's a keyword in JavaScript that I could use. An example of using this is I could say, okay, let's create this pair with my cons function, and I'll put 1 and 2 inside there. And then this is some unit test code from my JavaScript, and I'll say, I expect that if I get the car of that pair, it should be 1. Remember here, this is not the number 1, it's a function that represents 1. And if I ask for the could'er, I should get 2. But this is not a linked list. That's what we started talking about. So the second example is my linked list. I cons 1 with the cons of 2 with the cons of 3 and a nil. And so you could think of this like I've got this thing that has 1 in the front, and then the tail is all this other stuff that has a 2, and its tail has the 3, and its tail has the nil. And so now if I say, give me the car of the list, I get 1. And if I say, give me the car of the could'er of the list, that gets me the 2, and similarly for the 3. And then if I just ask for the could'er 3 times, I get to the very end and I get my nil value. So just one more amazing thing you could do with Lambda Calculus with just some simple functions. Of course, when you're trying to test out your implementations of these Lambda Calculus functions in some programming language, it's very convenient to have a function you can call in your language that will give you an actual value that you can print. Like when I'm looking at 3, I don't want to see that what I got is a function that calls a function I pass it 3 times. I want to see the number 3. In JavaScript, you could write these kinds of functions. If I pass it one of my functions that represents true or false, it's going to give me back the actual JavaScript value for true or false, and I can print it like in a console log. Same thing for numbers. I give it some number, and what's happening here is that it is applying this function n times. Every time it happens, it starts with the 0 going in for x, and when I apply it once, I get 1, and then 2 and 3. And so I get back an actual number that I could print out for my testing purposes. So I have a list of resources you can go to if you want to dig into this further. The main thing I want to share, though, is that I do have all of this code in this GitHub repo. You saw me run those tests earlier. This is just showing you how to run those tests. Clearly, you've been successful in your programming career all this time, and maybe you never made any use of this or even thought about this. You don't need this to be a successful programmer in any programming language, but I think it's really cool to see what you could do if you're in this environment where all you have are functions and you don't have values like Booleans or numbers. And of course, you could use this knowledge to impress all your programmer friends that didn't listen to this talk today and didn't learn about this in school.